till the end of February. Yes, hello everyone, and thank you actually for giving me this time, because it's always great to talk about your work. And here I'm going to present our project on Elbrus mountain, and this is our, let's say, baby, because otherwise how can I call the project? We've been working since 2004, and that was the first deep drilling accomplished by Russian team. So some history first, and of course I'll start with, it's not just my talk. I'm going to make a review of our results so far, and of course, as all other ice core drilling projects, that's a large number of people is behind that project. Mainly it's the Russian-French project, so half of the core was analyzed in Grenoble and LGG, and also some of the analyses were made in St. Petersburg, isotopic composition, and also in Venice. And so the motivation, I'll put it as a geographical setting actually. So on this image you can see where all people live here in Eurasia and where the mountains are. And this is not the room where to talk about how important the ice cores from mid and low latitudes are. So far we have ice cores from the Alps and from, of course, Tibetan Plateau and from the Altai. And obviously there is a place here which is missing the ice core information, but at the same time the westerlies are the most important atmospheric circulation pattern here. And how does it change, and what do we see downwind from the Europe? That was the motivation to try to find a place to drilling in an ice core. And so this is where Caucasus actually is, and this is where Elbrus mountain is. I will show it to you later. So here we expect to have a signal from not only from Western Europe, but also from whole that region here, including the Middle East and the southern Russia and Eastern Europe. So before that, in the Alps, there was a number of ice core drilling projects, of course, and the main results were the reconstruction of the atmospheric aerosol load and the composition over the 100 years. I'm speaking of published results. So, and also it was shown the important role of Saharan dust in European cores, and the changes of sulfate and nitrates, and the maximum in 1980s, and then the gradual decrease towards the 2000s. Some results were obtained for the Swiss Alps too, and recent work on Mount Ortles, of course, we're expecting some new results from the Alps. But given the number of the ice cores, there are not that much of information actually available so far from the Alps. From the Altai, recent work by Eisen et al. Showed that there is the age of the glacier goes back to the Younger Trias, and there was the recent increase in temperature also showed, and some work has been done by Swiss team also on the atmospheric pollution in the Alps. So now we go to the Elbrus mountain, and that's how it looks from the International Space Station. So this is the volcano, and this is actually active volcano. I mean, it's a dormant volcano, but the most recent eruption was about 2,000 years ago, just 2,000 years ago. And it dominates the mountain and the surrounding ranges. The first glaciological studies were initiated during the International Geophysical Year, but there were simple descriptions of the conditions, and basically said that the coldest conditions exist higher, which is an obvious thing to say. But nevertheless, there was some snow peaks and indication that on the highest parts, there could be a recrystallization zone, so no melting. And yeah, that's just to give you, we have mass balance measurement here on Garabashi Glacier, and yeah, glaciers are retreating faster and faster from, especially in the recent years. There was a period of actually positive mass balance in 1980s, but that followed by a dramatic decrease in 2000. Elbrus itself contains 10% of the whole glaciation of Caucasus. And this is how the mountain looks, and our work there started in 2004, and I was involved in that project. That's where we first got to that western plateau. It's located to the west of the western summit. This is how it looks, and it's above 5,000 meters, and it's pretty flat. And first work we did there was a shallow drilling of 2004, and the isotopes were analyzed. Actually, I will just skip to, no, I will not. Analyzed here, and then we did also some GPR measurements in 2005. We installed the automatic weather station, and finally in 2009 we drilled the deep core. It's a proper climb. It's not the most toughest climbs, but it's high up. But the good thing about Elbrus that helicopters still can operate in that altitude, and they can bring all the load to the plateau. So once again, that's how it looks. That's the plateau, and that's the Black Sea just here, and the Caspian Sea here. Climate, here you see some data from meteorological stations, and there's pretty evenly distributed precipitation through the year, with the maximum in the summer month. And this black line is actually data from our weather station, which we lost unfortunately after just 4 months of work. Nobody knows what happened to it. It was either stolen or just buried under the snow. We don't know. We were trying our best to find it, believe it. But this just actually, we used that data to correlate the temperature with the reanalysis for a 550 millibar surface, and it fits quite well. And these are data from other meteorological stations, and you see, so the temperature here somehow reflects the regional patterns of temperature. Just to give you an idea about atmospheric circulation, this is the visualization of weather, and it's just 2 days ago. So you see sometime we have this flow from the south, and if this is the different pressure levels. So this is 700 millibars, so about 4,000 meters. This is 500. This is where we are at 500 meters elevation, I mean. Sometime during the winter especially, you can have an inflow from the north straight, from the Arctic, but mostly it's westerlies. And this is the typical pattern of the summer and spring. So the results, these isotopes were measured here, actually in Bird Polar Center. And first, when we got this record, so it's very cold place. It's minus 17 degrees Celsius, and there is no melting, just a very narrow ice layers, probably due to the insulation. And the isotopic range was close to the coldest mountains so far. So it just gave us an idea that this is the very good place and a good seasonal signal variation. The ice thickness, we found the depression here, and this is probably the ancient crater of the Elbrus, which was unknown for that. And actually that's the thickest ice which exists on Elbrus, because in just 2 years ago we measured all of the Elbrus glacier with the helicopter, and still this is the thickest glacier here. So we wanted to drill close to this deep part which is 250 meters. Once again, that's how it looks. So it's just, this plateau is open to the west. So all the air masses are coming and depositing the snow. So this is a very good location. The drilling took place in 2009 in August, September. It was, because of not everything goes according to plan, of course. So the helicopter landed in a different place. We were waiting for that for 2 months, and people had to go out. And at the end, there were just 3 people drilling, actually. But they drilled to the bedrock, 182 meters. Core was transported frozen state to Moscow, and then half of it to Grenoble. This is the density, and this is the temperature. And actually, the first result was obtained for a geologist. And they used our temperature record to calculate the temperature and the location of magma chamber of Elbrus, and they showed that it's actually quite close to the surface, and it's very warm, it's liquid, so it is an active volcano. This is how the bubbles look, and that gave us an idea that we may try to measure the air bubble, well, the air contents in the bubbles too. And we did, but it did not still yet worked out, and I will explain why. So in Grenoble, they measured the major ions, some of the organic compounds and acids, and also we used the CFA, the continuous flow analysis system in Grenoble. So there were 2 sets of sample. One is discrete sampling, traditional one, and another one by using the CFA. And also the black carbon was measured using CFA, and the dust was measured using the Abacus instrument and the CFA, and some of the levoglucosan measurements also being done. So that's how the record looks like. You see the clear seasonal signal here, and that's actually quite an impressive one. And we also drilled 4 shallow cores to check whether there is a wind transport and wind relocation of the snow, and apparently it is not that important here compared to the other places in the Alps. So we're not losing the winter precipitations here, which is great. And this is just this core gives an opportunity to reconstruct the conditions, at least for several hundred years, with a seasonal resolution, which is the advantage of this core. So we used 2 species, ammonium and succinic acid, to date the core and to actually to get the summer and winter layers. Because sometimes isotopes are actually showed the increase were enriched during the still winter month, probably due to, I don't know, precipitation which came from the south, because the Black Sea is quite near, so sometimes we have this effect of the moisture source rather than the temperature in isotopes. But when we go deeper, the seasonal signal decreases, and so far we can confirm that for 150 years we have a seasonally resolved record, which is at least twice more than they used to have for the Alps. So the dating was made by annual layer counting, and also tritium peak, which is here, and this is 1963. And we also found the Katmai eruption. It's actually here. You see that it's acidified layer, and it's high sulfate composition, unlike other sulfate here, which are alkaline, so they are dust layers. We found also 3 other volcanic, well, it's suspected to be volcanic layers, tephra layers, One of them is attributed to Consanguina eruption, and another two, they are actually unknown. And it is also possible that we have actually the footprint of Elbrus itself, because when you're there, you can actually smell what you can smell? Sulfate, yeah, sulfur, and because just over here you have this sulfur rocks just coming out, and actually over here there are hot, not springs, but there is a hot spot just under the glacier, and it's very interesting because above 5,500 meters you have a moss growing there, and it's plus 42 degrees Celsius just on the surface. That's where we melted some samples to. And yeah, so another dating was done by modeling, and you see here how the layers of the, well, you see here that the most ancient ice, of course, in that deeper depression, but unfortunately, due to logistic, we couldn't move the camp there, so we drilled where the helicopter landed. But still, there is an opportunity to have a seasonal record up to at least thousand years if we drill deeper here. So now I move straight to some results, and first is the isotopic compositions. That's how the record looks like, and here you see the different colors are the different shallow cores and the deep core, and they reproduce each other very nicely actually. Even the details are there. We also did the measurements in International Atomic Agency, and have the same basically results, and from the new lab in St. Petersburg. I will skip straight to what we found so far. I mean, it's ongoing work. All of it, what I'm showing now, that's the PhD student working now on that project. It was not straightforward actually to find any correlation with the isotopes, but because we don't know when the precipitation is happening at that plateau. So many times when we were in the field there, you have a snowfall, there is no snow in the valleys, or you have a rainfall in the valley and we have a clear sky for a week, and everything is just covered with clouds. But nevertheless, with the summer temperature and summer warm season isotopes correlate quite well. Apart from the recent years, because we don't see enrichment in the isotopes, unlike the temperature records show us. In recent years, we don't see that. But what we see, and this is a little bit surprising, the increased enriched isotopes actually in the beginning of 20th century, which was supposed to be little ice age, but apparently the summer temperature were comparable at that elevation at least. And the winter isotopes negatively correlated with the North Atlantic oscillation, which actually was expected because the stronger North Atlantic oscillation you have, the more southern path it goes, so the warmer isotopes you will expect. Not the warmer, the heavier isotopes you would expect in the Elbrus core. Refractory black carbon. I'm saying refractory because it's very important to distinguish, because all the definitions of black carbon is somehow confusing, and you cannot compare actually directly the records which were obtained by different methods. They can be of orders of magnitude different. But so this is the refractory, this is how black carbon looks. And this black carbon is defined by its that it's insoluble and it vaporizes at temperature near to 4000 Kelvin, and also by its absorption of light. And so far for the Alps, the records were pretty limited. Information about black carbon. Yeah, it's quite popular now, but so far there are no actually long records of black carbon, and somehow they contradict to each other. For instance, this one is from Fischerhorn core from Swiss Alps, and there is no increase at all in 80s. And that's the record from Elbrus we have from the CFA, so it's very detailed. And we actually made it longer by using the shallow core of 2013. And I will just show you. So clearly there was this increase in 1980s, but the highest peak was found in 2003. And we actually thought, well, that matches quite well. That's the second world war in Iraq. And that's probably due to the fires of the oil plants and stuff. And so we considered that, but then we measured the leverglucosone, and it told us that that was the forest fires. So the elevated leverglucosone tells you whether it was from the biomass burning or not, and that was from biomass burning. And we made the back trajectories, and there was the large fires in 2003 in Spain that time. And we believe that's exactly the signal we see. We tried also to compare our results for the footprint of different regions. So this is a little bit tricky, but it's not actually. So you have these different regions here. You use the back trajectory model, and you try to estimate what percentage of these trajectories during the year or particular season are coming to Elbrus, to the drilling site. And we ended up that 64% is actually coming from this. It's called Eastern European region, but it actually includes Middle East too. And then, of course, the further you go, the less you have. And then that percentage was multiplied with in black carbon emission inventories, which exist for every country. And by using this approach, we can sort of compare results from the inventories with our record. And what it told us that, they are different, and inventories underestimate first the emissions of 1960s here, and also the recent increase actually in the emissions of black carbon, which can be probably related to the increase in production in Eastern Europe. Well, this is something, I mean, we state that just that the inventories are not reflect what we see in the core. Dust, that's my specialty, so I can talk a bit longer about it. The Elbrus is influenced by these large dust deposition events from the desert. And this is just an example of 2009 snow pit, and that's 4 huge dust horizons, and that's one of the events. That's this horizon here. That's 5th of May 2009, when literally all the mountain was covered with the yellow dust. And that dust came from both Sahara and the Middle East. And in the core, from now and then, we see those large layers. So what I did is I used the whole different methodologies, including the satellite imagery, the meteorological analysis, back trajectories, Calliope satellite, LiDAR missions, to try to pinpoint the dust sources and to track back each individual dust event, and which resulted in the dust deposition in my shallow core of 2013. and try to understand what are the dust sources. To illustrate how you can actually do that, this is a animation showing the Severi imagery, which works in infrared, and in this pink color, that's the dust cloud. And you can literally see where it's coming from, and because it's so high time resolution, it's every 15 minutes, you can track the dust cloud and how it affects the cloud formation and exact time when it was deposited on glacier there. And so we know exactly where it came from and when it was deposited, and using that technique was able to really point the major dust sources, at least for those 5 years, which were found in shallow cores. Also, by using that shallow core and Coulter-Counter analysis, we measured the dust flux and all the averages, but more importantly, those large peaks, those 4 peaks, that's the 4 horizons in that snow pit of 2009. There is another one, 2008, and this is exactly the event I showed on the animation, and that peak coincides with that 22nd of March deposition event, and the dust came from Sahara, so that we know for sure. But for the deep core, we didn't use the Coulter actually counter. We used the CFA, the Abacus instrument. And just a quick word about methodology. So the Coulter counter uses the resistance, changes in the resistance in the electrolyte, so it counts the particles, and it also, resistance depends on the volume of particle. But in a Abacus instrument, that's the laser beam which is goes through the glass window and received by detector. So when you have more than 2 or 3 particles, sometimes you can have the coincidence of these particles, so it will count as 1 particle. So here you can see the data from red from Abacus and black from Coulter counter. So what you can do is actually you can just calibrate it like that. And that's what we did. And so all the Abacus data are calibrated. But still, those large peaks are underestimated by the Abacus. The rest, just the consistency of the data. So the calcium is a very good tracer for dust, especially in the summer. And for you see the correlation for summer and for annual dust concentrations are very high. And these are a number of different records. They all fit quite well one to another. And this is the dust record from the Elbrus core we have so far. So that's the calcium and that's the dust. And you see there is a trend of increase of dustiness of the core since the beginning of 19th century. And obvious question was why and how we can compare to it, whether it was the change in dust sources strength, or the wind changed, or atmospheric circulation, or I don't know. So I was trying to find what record I can compare it to actually. Unfortunately, there is no record in the Alps which I can compare. Well, I hope that in the Oort list they will have the dust record. But believe it or not, given the tens and dozens of ice cores obtained in the Alps, there is no dust records from the Alps. And so there was the paper by Natalie Mahavold, Observed 20th Century Desert Dust Variability, and that's what they have for North Africa. And there's not a lot of data in that paper, I must admit. It's all based on modeling and 2 or 3 paleo records of dust. And this is the region they used, Middle East and Central Asia, everything. Everest, Dasupo, everything. And of course it's all different. If we compare it to Elbrus, well, there is some similarity here with North Africa, with increase, but actually it's not that good. So what I found recently was the paper of 2016 and actually 2015. It's so-called the Old World Drought Atlas, which was made based on 120 true ring chronologists all around the Mediterranean region. And they made a half-degree grid of PDSI, which is Palmer Drought Severity Index, which is the measure of dryness of the territory, for the whole Mediterranean for 900 years, actually. And it's available online. And they showed in their recent paper that Mediterranean drought in recent years was the most severe over the 900 years, actually. And so what I did, I looked more closely to this region here, because that's exactly where we have the dust sources. Well, we have it in Sahara too, but that's more frequent dust sources here. And indeed, those 2 years, that's first actually got my attention, because I was considering those 2 years as a mistake in the data, 1992-2000, because it was so much dust in here, and I couldn't find the why. But here, in that particular region, there was the most severe drought at that time. And so the data from the core, the dust data from the core, correlate very well, at least for recent years, with PDSI, with the drought index from the Middle East. And that just gives you an idea. Well, first of all, we confirmed that, yeah, there is an increase in the dust, so probably there is a increase. Well, the driest condition exists in Middle East. And secondly, that we can reconstruct it even further back and to see how it changed over the time back there. Just to illustrate that how those 2 years looked like. And that drought was really severe. And so concluding remarks, that the Elbrus record is very, very valuable, and we can compare it to the Alps and extend our reconstruction and understanding of the atmospheric variability and atmospheric circulation in this region, because there's not much data exists actually. But there are still some problems, and first problem is that we don't have any ice left from that core, because half of the core was sent to France and half of the core was supposed to be an archive, but yeah, we lost it because of malfunctioning of the freezer. So that's why it's very important to keep your freezers in good condition. But we applied for a new drilling project for this deeper part, and we hope to get it and to have a longer record and a better record too. These are some publications, and more publications are coming next years. And I thank you very much. And if you have any questions, I would love to answer.